Hello everyone, welcome back to the relevant session. So we have been discussing solidification and stabilization, right, in the context of remediating contaminated soils or sediments, yes. And what is the relevant principle here that we are looking at? We are not, we typically do not, degrade the contaminant or such. What are we trying to do? We are trying to see to it that the contaminant stays where it is, let's say, right, or is not transported to a greater extent, let's say. Maybe you can think of this as containment, but you are not putting a barrier around it or such, but you are building a relevant or you are transforming the relevant solid, let's say, right. And how are we doing that? Again, by solidifying it, right, say. So solidifying it as in we are improving the physical strength or physical characteristics of the relevant material, right, or the structural integrity, if I may say so. And then stabilization, right. And stabilization, what are we looking at? We are trying to make the contaminant immobile, right, again different ways. So depending on the contaminant, sometimes we can also try to add admixture so that you are going to be able to degrade the contaminant. But generally though, we are only looking at solidification and stabilization and not degrading the contaminant too. So within this context, we looked at, let's say, how we add various binders, right. We need binders, and what are some of the binders that we typically look at? I think we looked at obviously cement, and then fly ash, right, and then there are other cases like blast furnace slag and so on and so forth. But depending upon the type of contaminant, you might go for them, or depending upon their availability. But typically we choose cement or fly ash. Again, what's the principle here? Cement is rich in calcium and silica, let's say, and once you add water and it's hydrated, you have the CSH matrix being formed, and that's what more or less I believe gives strength to your particular what we say cement now once it hardens or is hydrated, pardon me, right. So CSH matrix is what you are trying to form. So what is the role of fly ash here? Typically fly ash is rich in silica. Depending upon the type of coal, it will either have some or sufficient calcium or no or little calcium. So in that context, you will either have to add lime for source of calcium, or that, let's say, you will also add cement, some fly ash and water, because as we saw in the relevant reactions, let's say, as you added or hydrated cement with water, calcium hydroxide was being given out, and that calcium again can be a source for the CSH matrix when you have fly ash present, right. So typically you can to reduce the cost, obviously add cement, fly ash and water, and again sometimes water you might need to add that additionally, or the water present in the relevant waste itself will need to be taken in, right. So that's something that we have looked at, right. Again, we looked at some aspects and a few minor what do we say examples where these particular aspects were implemented. As in, we looked at two cases when we had either a shallow excavation, not excavation, pardon me, yes, I believe excavation, and then ex situ solidification and stabilization, and then one where we had to, or the relevant people had to look at solidification for up to a depth of almost 20 feet now, right. So we looked at three different examples now, right. So in this context, with respect to the contaminant what do we say transformation or contaminant reactions, right. So as we what do we say solidify and stabilize this waste, how is the contaminant going to be transformed, right. We briefly looked at some of them, but today we will look at that in greater detail and move on to solving the relevant examples, let's say, right. So obviously you are adding lime, right. Again, as you see, or if you looked at the relevant reactions, you typically see that the pH typically increases, typically again, right. Again, we will look at that in greater detail in the example. So again, obviously pH, as we know, is a master variable, and most of our environmental engineering related aspects are scenarios now, right. So how does that particular pH or the master variable play a role here now, right. So here obviously we know that or we briefly discussed that the contaminant can be precipitated, or precipitation of the contaminant can occur, right. So how does that go about now, right. So let's say you have a particular heavy metal, let's say we'll take the example of a heavy metal in solution now, right. So let's say you might have observed, let's say maybe with chalk or sugar or salt, let's say in a particular glass, or a glass of particular volume, and if you keep adding salt or sugar and keep stirring that, after a particular point, let's say, you know, any other additional salt or sugar that you add is going to not dissolve further, right, or it's not going to be inside the solution, not inside solution, dissolve, I guess, right, but it will precipitate out or you know, settle to the bottom, if you might have observed that, right. Again, what's the key here? That the key is that a particular solution can hold only a certain concentration of the relevant species, or you know, there is a maximum concentration with respect to the relevant dissolved concentration or the aqueous concentration for different particular species now, right. So here we are going to look at how we understand this layman's term of maximum concentration, what are the variables that affect it, and so on, right. For example, now we are looking at lead, right. So lead can, let's say, again OH minus in water. So this is my metal and this is my ligand, let's say, electron rich, this is electron rich and this is electron poor, right. Again it can form, okay, and this can precipitate out. S means a solid which can precipitate out, right. So this is something that can happen out there. And again, for a particular example of lead here, obviously you have other examples of different heavy metals precipitating out with the ligand OH minus, or different ligands that might be present in water now, right. So again, OH minus is always present, so that's the reason we are looking at this example now, right. Here we have the precipitation, but typically we write the reaction as dissolution reaction. So PbOH twice the solid will be in equilibrium with Pb2 plus. What does this mean again? What are we writing now? We are writing the equilibrium relationship here, right? 2 OH minus, right? So it will, this is the equilibrium that's you know, going to prevail, let's say. Again, there are different stages for precipitation. It's not as if, let's say, once this particular solution is slightly oversaturated, you know, precipitation is going to kick in. It's not going to happen like that. There are different stages in there, but we are not going to go into that detail for now. But again, keep in mind that the solution needs to be oversaturated or considerably oversaturated initially for precipitation to kick in. Again, we are not going to go into that in that detail now. So again, this is called, let's say, the dissolution reaction. I guess that's self-explanatory, right? Dissolution reaction, right? Or if I come back to this, for a given concentration of lead, let's say my particular solution is contaminated with lead now, right? That's what I have here. And you know that lead is in equilibrium with PbOH twice the solid and OH minus now, right? So if I keep adding or increasing this particular OH minus, let's say, what's going to happen? The equilibrium will shift towards the right, right? Or the system would travel towards PbOH twice, or the solid will be formed now. So while the solid is being formed, what will happen to the Pb2 plus concentration in the water? Obviously it's going to decrease, right? So by, you know, changing the OH minus concentration, I can affect the concentration of the relevant heavy metal in that particular solution now, right? Again, for this particular example anyway. So again, as you can see, by increasing the OH minus concentration, what does that mean? By increasing the pH, right, I can precipitate the lead out here, right? So again, let's come back to the dissolution reaction. So we typically have the equilibrium constant for this reaction. We refer to that as the solubility product, KSP. That's equal to, obviously it's the activity of the relevant reactants raised to their stoichiometric coefficients, right, by activity of PbOH twice the solid. Solid activity, again we look at mole fractions here, right, and mole fraction, again if it's a pure solid, so the activity of this particular denominator term or the PbOH twice solid will be equal to 1, right. So that's why this is going to be Pb2 plus, activity of Pb2 plus into activity of OH minus to the power of 2, right. So if I assume that the solution is relatively dilute enough such that ionic strength doesn't play a role, or that, what does that mean? That means that I can approximate activity by the relevant concentration, right. As you might be aware of, activity is going to be equal to the activity coefficient times the concentration. This is activity here, this is the activity coefficient, and this is the concentration, right. So for example, if the solution is dilute, I can say this is relatively equal to 1, and that activity is more or less equal to or can be approximated by the concentration now, right. So, that is what we are going to assume here. Again, what does activity give an idea about? It gives you an idea about, or activity gives you an idea about the ability of the relevant compound to react, let us say, right. So, that is what we have out here. Again, so it is OH minus times to the power of 2. So, that is what we have here, right. So, this is a constant, Ksp is a constant, right. So, as you can see, this is how the equilibrium relationship this is the equilibrium relationship, pardon me, and here we have that Pb2 plus aqueous concentration in equilibrium with the OH minus concentration here, right. So, as you see, as you increase the OH minus concentration and such, the Pb2 plus needs to decrease, right. If I keep increasing the OH minus concentration to keep the Ksp to be constant, it is a constant, right. What needs to happen to Pb2 plus? Obviously, that needs to decrease now. But again, keep in mind that it is not as if I keep increasing the pH till 14 and I end up with the maximum removal, or not every, pardon me, almost all the Pb2 plus or lead precipitating out. Why is that? Because we just looked at precipitation. This is something that obviously can happen within your or during your solidification stabilization. And why can't I just take the pH up to 14 and say that okay, OH minus is maximum there, and then I am going to have relevant what do we say, the maximum removal of Pb2 plus from the what do we say, aqueous phase anyway. Why is that? Because the metals can also form complexes, right, and these complexes are typically very much soluble. So, what happens is, as I keep increasing the OH minus, right, there are other complexes, or there are complexes that can be formed, let us say plus 3 OH minus going to, let us say, Pb OH thrice, and I think that is a negative charge. This is not a solid now, this is a complex here, right. So, if I keep increasing the OH minus simultaneously, let us say, when compared to this particular reaction where Pb2 plus is precipitating out, right. Here I see that it is precipitating out, here it is the complexation occurring. Obviously, both of them are going to occur simultaneously. So, once I reach a certain threshold for pH and still keep increasing it further, right, Pb2 plus or lead will end up being more soluble. Obviously, why is that? As you see here, there are complexes that the lead can form with hydroxide or OH minus that are more soluble, right. For example, at a certain pH or until a certain threshold, as you can see, lead can precipitate out, right. But as you can also see here, it is not as if I can just take the pH up to 14 and assume that everything is going to precipitate out, because you have simultaneously complexes of lead that are formed which are more soluble, right. So, that is something to keep in mind. Why is that? Again, try to understand this. So, this particular precipitation step depends upon the concentration of Pb2 plus that is in the solution, right, Pb2 plus, not any other complex or such. But what is happening simultaneously, let us say, this Pb2 plus and 3 OH minus, they form a complex. So, it is not as if Pb or lead is present as the free, what do we say, in its free state, not free state maybe, and it is as in its ionic phase, let us say, right. As you can see, it is in the form of a complex. So, thus Pb2 plus will be lesser, but the PbOH, what do we say, lead is still present as a complex, which is again in the dissolved phase, right. So, that is something to keep in mind. So, complexes can be formed. So, typically let us say if I look at this and if I say this is the concentration of the compound in aqueous phase or in the water, let us say, and this is the pH. So, what is going to happen, let us say, as I keep decreasing the or increasing the pH from this particular reaction, I see that the concentration of lead, let us say this is for lead, let us say, right, keeps on decreasing now, right. But once I hit a certain threshold, let us say 12, 11, I am not sure what it is for lead, but we can check that, right. What happens is that you again have an increase in concentration of lead. So, here it is the total concentration, if I can say maybe. And why is this increase? Why do I see this increase in concentration of lead with after a certain point and this pH, let us say? Why is that? Because complexes are formed in this particular region, let us say, right, or the lead in the form of complexes is relatively more compared to the lead that precipitates out. So, that is something that you see. Again, this is from the relevant theoretical aspects, right. But looks like in practice the situation is slightly different, as in you have something like this and something like this, and then slight increase, pardon me, right. So, this is again same graph pH and total concentration here, right. Again, this is typically the real world behavior, and it is obviously because you also have other materials present out there like cement and such in your what do we say, during your solidification and stabilization. It is not just lead and hydroxide and so on. So, the real world behavior is slightly different, but obviously you will make your calculations based on theory and then look at the lab tests and then take that forward. Obviously, I am not going to jump right into practice, let us say, from just my theory, but obviously the theory is going to be the basis for building the relevant aspects, let us say, right. So, again we looked at how the contaminant can precipitate out, how it can form complexes, right. So, the other aspect is it can also be adsorbed, let us say, right. So, depending upon, let us say, either the admixtures that you put in, let us say, or even that you have the CSH matrix and such, the compound can be adsorbed onto the relevant what do we say, solid phase here, right. So, that is one way. Obviously, again you can think of it slightly similar to the NaPl or the organic compound, let us say, adsorbing onto the organic fraction of the soil and so on. So, again adsorption can occur here, right. Again depends upon different types of aspects, as in what is the media here, let us say, and what is the type of contaminant and so on and so forth. And the next case is, well, we always will have, or not always, let us say, we can have the redox reactions, right. So, some compounds, let us say, obviously can what do we say, be or become less toxic by relevant reduction or oxidation. So, obviously for that you will need to either provide the electron acceptor or electron donor, right. So, redox reaction more or less, obviously not more or less, it involves the transfer of electrons, right. So, what do you need for redox reaction to go through? You need an electron acceptor, a compound, an electron donor, right, and then the redox reaction goes through. So, electron acceptor, let us say, if I say A plus B, let us say, electron acceptor is typically the more oxidized form and this electron donor is typically the more reduced form. What will this lead to? It will lead to formation of B, which is relatively more oxidized, and A, which is relatively more reduced now, right. So, one of these, let us say, can be your contaminant. Let us say A is your contaminant, and its oxidized form, it's, let us say, relatively toxic to your to either the environment or humans, let us say, right. And thus, let us say I want to reduce this. So, I can add an admixture, let us say, which is a reducing agent, which can degrade A to its reduced form, right. So, again what do we need here though, and as you can see in your redox process, you need an electron acceptor and an electron donor, right. It is because unlike H plus, electron cannot what do we say, exist freely out there, right, or it can't accumulate now. For the redox process to go through, you need to have an electron donor and electron acceptor in proximity, right, for such that the electron transfer takes place, right. So, again you can add different admixtures, let us say, and let the redox process take place and go through. And second aspect is, let us say, it can be incorporated or incorporated it as in the compound, incorporated within the matrix, right. As in you have the CSH matrix being formed, cement, fly ash and water. So, a part of this particular what do we say, contaminant can be incorporated within the relevant matrix. And let us say for organics, let us say, what can we have? So, we can have, let us say, base catalyzed degradation, let us say, if I can call that. So, thus a part of the organic compound can be degraded, let us say, in the presence of what do we say, the base, let us say OH minus, let us say. So, that is something that typically happens in this context, especially if you maintain the pH to be relatively high, right. So, let us look at the other aspect. So, we can have reductive dechlorination. So, similar to the case when we looked at, I believe, either natural attenuation or PRB and so on, let us say, if you have an organic compound that's, let's say, a chlorinated solvent, let's say, right, or such, obviously that's a relatively more oxidized form of the organic compound, right. And what can you have? Obviously, depending upon the admixtures that you add, you can have reductive dechlorination, right. So obviously, you need to provide now, what do you need to provide? You need to provide the electron donor, because the organic compound that's chlorinated is the electron acceptor, right. So that's something that can happen now, right. So these are the ways, let's say, how the contaminant can be transformed, or the relevant contaminant reactions typically occurring within this or during this solidification and stabilization, right. So now let's look at transport, let's say, right. Transport of the relevant contaminants, right. So obviously, what's one way that the contaminant can be transported? It's obviously by advection, right. As in, let's say, you have your solidified and stabilized monolithic blocks here, let's say, right, and either rainfall or any other leachate coming in contact with it, right, or even flowing through it, let's say, because there will be considerable pore space. As you know, cement, once it hardens too, right, you will have considerable pore space, right. You know, you are going to have the leachate coming in contact with your relevant what do we say, compound now, right. So if it's in the aqueous phase and such, let's say, you know, your compound is going to be transported along with this net flow of fluid, and that's more or less advection now. So in this context, what is it, what's something that you want to aim for, especially with respect to the porosity and thus, let's say, the permeability, let's say, of the relevant solidified and stabilized mixture. You want it such that, let's say, the porosity or even permeability, right, to be lesser than, this is the porosity of your mixture, let's say, should be less than the porosity of the surrounding what do we say, material now. Why is that? Because let's say if the porosity of these blocks, or this, let's say your leachate is coming out here, and the porosity in here is relatively less than porosity in this media surrounding it. So what is the water or the leachate going to do? It's not going to, it's going to take the path of least resistance. So it's going to flow around the solidified material rather than flowing through it, right. So that's something that you will aim for, as in with respect to porosity or the permeability of that particular block now, right. So again, keep in mind that advection is something that can typically or will take place, and the second aspect is by diffusion, let's see, right. Again, we know how diffusion works, let's say. Again, you have, let's say, your compound in equilibrium here again, right. Again, even if there is no net flow of fluid, and if you have, let's say, water in contact with this particular solution or the compound here in your solidified and stabilized matrix, right, you can have diffusion, as in, because the concentration is higher you know, at the solid or near the solid, and you know, less in the relevant leachate, let's say. Even though there is net flow, no net flow of the leachate, through diffusion the contaminant will want to be transported from here to out here, right. So that's something that you see. And upon what factors is this dependent now? So it's going to be dependent upon, obviously, the diffusion coefficient. Typically we are going to write the effective diffusion coefficient, taking into account the tortuosity or the retardation and so on and so forth, but typically we are going to take into account tortuosity. What is this tortuosity now? As in, similar to our groundwater case, let's say, you know, you are going to have different flow paths possible, right. So dispersion can take place, right. So again, taking that into account, rather than just having the diffusion coefficient, we are going to have the effective diffusion or dispersivity coefficient, I guess, right. Again, diffusion coefficient, what does this depend upon? For example, let's say, I think one example we might have looked at is opening a scent bottle here. So the person sitting at the back of this room can sense the compound, or smell it rather, right, after a certain period of time. Why is that? Even though there is no net transport, the compound will travel from here to there because of diffusion, let's say, right. Again, diffusion is random in nature, that's something to keep in mind, right. But if I keep this in, let's say, water, let's say, right, it might take less time, more time, depending upon the type of contaminant. Why is that again? Because you know, the diffusion coefficient depends upon both the media here is air, and the compound, which is the scent, I guess. So in the second case, the media is water, and again the compound is still the scent, right. So, this diffusion coefficient depends upon both the media and the relevant compound here, right. Again, that is something to keep in mind. And then the next aspect upon which diffusion depends upon is obviously surface area, right. Surface area or particle size and so on. Why is this important now? As in, you know that flux is equal to mass per area per time, right. So, this is flux, right. So, if I just want to know the mass flow or how much contaminant is leaching out per time, as in I want to know how much mass of the contaminant is leaching out per time, right. So, that is equal to the flux, let us say, due to diffusion into the area, let us say, right, or the total surface area available. So, if the greater the surface area available, the greater the chances for not chances, greater the diffusion, let us say, right. That is what something that you see here. So, particle size plays a relatively important role in this particular context now, right. So, again, with respect to transport, we need to look at advection and diffusion, right, and different aspects within here. Again, hydraulic conductivity, right, is an important parameter here. So, here in this context, we look at porosity, permeability, and obviously typically hydraulic conductivity, and again diffusion is obviously always plays a role, right. And what are the other aspects that we need to keep in mind? Obviously, we need to look at the physical integrity, let us say, or physical characteristics, right. So, how do we test for this physical integrity, let us say, of this particular matrix now, or your solidified and stabilized mass? You are going to look at the unconfined compressive strength typically, right, and typically I think EPA, the US EPA anyway, right, and that is obviously very good standard to typically refer to, typically anyway, right. I think it says that it should be a minimum of 50 pounds per square inch, right, the unconfined compressive strength. Obviously, this solidified block should be able to sustain its own what we say weight, let us say, and also any weight above it and any water or such, right. So, again, you need to have structural integrity, let us say, or your mass should have structural integrity, right. So, in that context, obviously, we need to look at the unconfined compressive strength, right. And another aspect here is that, again, maybe not greatly relevant in all parts of India, but depending upon where we are, let us say. So, this effects of freezing and thawing, let us say, right. As in, you are going to have this solidified mass, let us say, and let us say depending upon where you live, let us say, you know, you can have freezing of this relevant material, and then again thawing of this relevant material, let us say, right. So, during this time, obviously, there are going to be changes, because obviously you have water, changes in the structural properties of your material, let us say. Again, you have water, and again its volume changes when it is solid and when it is aqueous, or when it is fluid, pardon me, right. So, again, you are going to have issues with what do we say, the integrity of your particular mass, let us say, or the solidified and stabilized mass, and so that is something to keep in mind. Let us say the effects of freezing and thawing on this particular aspect need to be looked at, right. And then we are going to move on to leaching, but looks like I am almost out of time. So, we will just talk about this very briefly though, right. So, leaching is something we need to take into account, as in I want to know or want to be able to estimate, let us say, at least theoretically, the rate at which the or the mass that will leach out, let us say, a particular point in time, given that I assume that diffusion occurs, or maybe there are other reactions occurring, or so on and so forth, right. So, for that we will obviously have to look at what now? It is going to be a material balance, right, or mass balance again on the relevant compound, right. So, that is something we are going to look at in the next session, and then maybe we will not maybe, and then we will move on to looking at how do we, you know, see to it that I maintain a certain pH, or what pH do I need to maintain, right, and thus what is the water, cement and fly ash and the solid ratios that I need to add, and so on and so forth, right. And I guess with that I will end today's session, and thank you.